Welcome back to Linear Algebra. I'm Dr. Jeff Groh. Today we're going to talk about the null space, range, and the Dim-Dom Theorem. First, let's define what we mean by null space and range. The null space of a linear transformation T mapping from vector space V into W is denoted by either n of t or maybe even null of t, and defined by the following. The null space of T is the set of all V lying in the domain space so that T of V maps to the zero in the codomain space. By way of a picture, suppose we have V over here. We have our linear transformation T, and we have W over here. Now, we're going to have the zero vector in W here. Everything that gets sent to the zero vector is in the null space. The space itself maps to some subset of W called the range. We'll denote that by R of T. So for a definition, the range of some linear transformation is denoted by R of T, or range of T, and defined by it's everything in the codomain space, such that if V equals W for some V in the domain space, it's everything that gets mapped onto. Now, for a fact, that's not true for nonlinear functions, but is true for linear functions. Let T map V into W be a linear transformation. Then the null space of T is a subspace of V, and the range of T is a subspace of the codomain space W. By way of proof, for the first part, let U and V be elements of the null space of T. Note what that means. That means T of U is the zero in the codomain space, and T of V is also the zero in the codomain space. In order to show that the null space is a subspace of V, we need to show the two closure laws hold. So, check this out. Because of linearity, T will distribute across sums. And because U and V are in the null space, they get sent to the zero vector. And the zero vector plus the zero vector is, of course, the zero vector. But that means U plus V is in the null space. So the null space is closed under addition. Let's see if it's closed under scalar multiplication. We'll apply t to a constant times u and see what happens. Constants come out of linear transformations. And so we get the constant times the zero vector in w. But any rescaling of the zero vector is just the zero vector. Therefore, a times a vector in the null space is in the null space. Is the null space empty? Well, t of 0 in the domain space is the 0 in the codomain space. That implies the 0 in the domain space is in the element of the null space, and hence the null space is not empty. Therefore, the null space is a subspace of V. To this end, let V and W be elements of the range. What does that mean? That means there exists two things, let's say U and X, in V, such that T of U is V, T of X is W. Something has to map onto V and W if they are in fact in the range. We have to show that the range is closed under addition and scalar multiplication. Then let's look at T of U plus X. That is in fact T of U plus T of X, which is V plus W. That means there does exist something in the domain space that maps to the sum V plus W, and that implies V plus W is also in the range. Also, T of AU is A times T of U, which is A times W. And that implies AW is in the range of T. So the range is closed under addition and scalar multiplication. Is it empty? Also, T of the 0 in the domain space is equal to the 0 in the codomain space, and that implies 0 in the codomain space is in fact in the range, and hence the range is not empty. That's the end of the proof. For example, suppose that T of xyz is, let's say, 3x plus 2y minus z, x plus y plus 2z. Find a basis both for the null space and for the range. The null space is everything that gets sent to 0. So first, to find the null space, we'll find everything that gets sent to 0. That means we have to solve the system of equations. 3x plus 2y minus z equals 0. X plus y plus 2z equals 0. We know how to do that. Let's set up an augmented array. 3, 2, negative 1, 0, 1, 1, 2, 0. Let's do negative times row 2 plus row 1. Yields a new row 1. We'll have a 0 in this spot. Negative 3 times this plus this. Negative 3 times this plus this is negative 1. Negative 3 times 2 is negative 6. Minus 1 is negative 7. We still have 0 here. If we multiply through by a negative 1, negative row 1 yields a new row 1. and then switch row 1 and row 2, we'll have 1, 1, 2, 0, 0, 1, 7, 0. We're now in row echelon form. One more step, and we will have reduced row echelon form. We'll take negative row 2 plus row 1 yields a new row 1. Negative 1 times this plus this, negative 1 times this plus this, and there we have it. We'll assume that the variables were x, y, and z. Z is going to be some parameter t, then y will be negative 7t, and x will be 5t. That gives us vectors x, y, and z in the form t times 5, negative 7, 1. That means every scalar multiple of 5, negative 7, 1 is a solution to the homogeneous system of equations, and hence in the null space of our linear transformation. That means a basis for the null space will be the vector 5, negative 7, 1. The linear span of this basis will be the entire null space. Note that the dimension of the null space here is 1. Only rescalings of a single vector. A straight line through the origin in the domain space is the null space. I'm going to make a definition on the fly. The dimension of the null space of some linear transformation is called the nullity of that linear transformation. So the nullity is just the dimension of the null space. In this last example, the nullity is 1. Remember that our linear transformation mapped x, y, z onto 3x plus 2y minus z, x plus y plus 2z. This is in the form 3, 2, negative 1, 1, 1, 2 times x, y, z. The product of this matrix A times this vector v gives you the linear combination of the columns. That means the range is equal to the span of the column vectors. Since we have 3 column vectors in a two-dimensional space, we know they are linearly dependent. The question is, how many of them does it take to reconstruct this entire span? Well, take a look at the first 2 vectors. 3, 1 is not a multiple of 2, 1. Since they're not multiples, they're not parallel, which means they poke off in independent directions. That means these things span all of R2. To choose a basis for the range, all we have to do is we can either take these, we can construct the entire range, which is all of R2, by taking linear combinations of these two, or any other basis that we wish. We could choose another basis, maybe the standard ordered basis for R2. Any basis will do. I want you to note that the dimension of the range is equal to 2. We're going to define another term on the fly. The dimension of the range of T mapping V onto W, T linear, is called the rank of T. So in particular, in this last example, the rank of our linear transformation was equal to 2, since the range had a dimension of 2. In our next example, I'm going to define T, which maps P4 into P3 by T of F equals F prime. The derivative, which we have already shown, is a linear transformation. I want to find the rank and the nullity, and also a basis for the null space and a basis for the range. So let's find the null space first. It's everything that maps to 0. T of F is F prime is 0. What functions have derivatives equals 0? We proved a theorem in Calculus 1 that the set of functions that have derivatives equals 0 is exactly the set of functions that are constant. If you take the derivative of a constant, you get 0. If you have a function that has derivative equal to 0, then that function is constant. It turns out that the null space is the set of all f such that f of x is identically equal to a constant for some constant a. That means then that a basis for the null space out of the space P4, polynomials of degree 4 or less, will be the number 1. All constants times 1 will be these constant functions, and that will span the entire null space. That then gives us the nullity equals 1. The dimension of the null space is 1. Now, let's look at the range. The range is the set of all polynomials in P3 such that T of F equals P for some F in P4. What polynomials in P3 have something that has derivative equal to that for some function in P4? Here's what we'll do. Let A plus bx plus cx squared plus dx cubed be in P3. Then, isn't it true that T of ax plus bx squared over 2 plus cx cubed over 3 plus dx to the 4th over 4 is equal to that? And this polynomial inside of this function t is an element of P4. That tells us then that an arbitrary element of P3 will be in the range. There will be something in P4 that maps to it under the derivative operation. What is the rank? It's the dimension of the range. P3 has dimension 4 because you have 4 independent constants, a plus bx plus cx squared plus dx cubed. You have to remember to start at degree 0, the constant term. You have 4 independent parameters. You have a 4-dimensional space. So the rank is 4. Notice that the dimension of the domain is 5, and rank plus nullity is 4 plus 1 equals 5. That's the dimension of P4, the domain. In our last lecture, we mentioned the following theorem, but we didn't prove it, that a linear transformation is completely determined by its action on a basis. Let's state that in a slightly more formal form and also that informal form. In other words, let B equals V1 through Vn be a basis for V, and T maps V into W. Then the range of T will be the linear span of T of V1 through T of Vn. Now, to prove the equality of two sets, you usually do the following. You prove one side is a subset of the other, and then you prove the subset inclusion goes the other way. The other side is a subset of the first. Prove subset in both directions gives you equality between sets. First, we'll prove subset inclusion in this way. To this end, let W be an element of the range of T. What does it mean to be in the range? It means there exists V in the domain space such that T of V is equal to W. But V is in the domain space, so it can be expressed as a linear combination of elements in the basis for the domain space. There are unique constants C such that V is C1V1 through CNVN, and that implies that T of V is C1 T of V1 through CN T of Vn, and that implies that W is in the span of T of V1 through T of Vn. We need to show set inclusion goes the other way as well. Let W be an element of the span of T of V1 through T of Vn. That implies W is C1 T of V1 plus Cn T of Vn for some constant C1 through Cn. But due to the linearity of T, we can rewrite that as T of C1 V1 through Cn Vn. But that means that W is the image under T of some element of V. That gives us set inclusion in the other direction, and that completes the proof. In our next example, we're going to let T be a linear transformation from R3 into R3, and let B equal to V1, V2, V3 be a basis for R3. Let's suppose that T of V1 is 1, 1, 0. T of V2 is 0, 1, 1. And T of V3 is 2, minus 1, and then minus 3. I want to know, A, is 0, 0, 1 in the range of this linear transformation? Well, we know that if it is in the range, then there has to be some linear combination of v1, v2, and v3, where the action of t will give us 0, 0, 1. If so, then there exists, the backwards capital E means there exists, some vector v in R3 such that t of v equals 0, 0, 1. But every vector v in R3 can be expressed in terms of the basis. So v is c1 v1 plus c2 v2 plus c3 v3 for some c1, c2, and c3. It follows then that 0, 0, 1 will be t of v. That's t of c1 v1 plus c2 v2 plus c3 v3, which is c1 times t of v1, which is 1, 1, 0, plus c2 times t of v2, which is 0, 1, 1, plus c3 times t of v3, which is 2, negative 1, 3. Do such constants c1, c2, and c3 exist? To find out, we need to solve this system of equations. My calculator gives me 1, 0, 2, 0, 0, 1, negative 3, 0, 0, 0, 0, 1. We get the equation 0 equals 1. That's inconsistent, which means no solutions, C1, C2, C3 exists. So the answer is no. 0, 0, 1 is not in the range of the linear transformation. On part B, I want to find a basis for the range of this linear transformation. To this end, note that it has to be the span of these columns. But note that 2 times 1, 1, 0 minus 3 times 0, 1, 1 is equal to 2, negative 1, negative 3. The last vector can be expressed already as a linear combination of the first two. It doesn't contribute anything to the span. So we can toss it out and still span the same collection of vectors. So the range is the span of the first two vectors, and the first two vectors are linearly independent. So we have ourselves a linearly independent spanning set for the range. That gives us a basis. We'll set B to be the set that contains 1, 1, 0 and 0, 1, 1. That will be a basis for the range. That tells us then that the rank of this linear transformation is 2, since the basis has 2 elements. Next, find the null space. To find the null space, we need to find everything that maps to 0. We need to find solutions to T of C1 V1 plus C2 V2 plus C3 V3 equals the 0 vector in R3. That means C times 1, 1, 0, C1, plus C2 times 0, 1, 1, plus C3 times 2, negative 1, and negative 3 equals 0, 0, 0. Solve that system of equations. To this end, we have the augmented array 1, 1, 0, 0, 1, 1, 2, negative 1, negative 3, and then 0, 0, 0. What is the reduced row echelon form? My calculator gives me 1, 0, 2, 0, 0, 1, negative 3, 0, 0, 0, 0, 0. You can see that if C3 is governed by the last coordinate, then C3 will be arbitrary. C2 will be 3 times C3, or C3 times T, and C1 will be negative 2 times T. That means everything of the form negative 2, 3, 1 times T will be in the null space of T. That means every scalar multiple of negative 2 V1 plus 3 V2 plus V3 will equal the null space, everything of this form. Recall, the rank was 2. The nullity is 1. The rank plus nullity is 3, and that's the dimension of the domain, which was R3. We've been getting at something called the Dim-Dom Theorem. It goes like this. Let T map V into W be a linear transformation. Then the rank of T plus the nullity of T is equal to the dimension of the domain, hence Dim-Dom. The dimension of the domain is the rank plus the nullity. Remember, the rank is the dimension of the range. The nullity is the dimension of the null space. The proof goes like this. Suppose n is the dimension of the domain space, and B, which is V1 through Vk, is a basis for the null space of T. Extend B to a basis for V. Let's suppose we have B hat. It starts off with the elements of B, V1, V2 through Vk, and then we have other elements, Vk plus 1 to Vn. Since the range of T is the span of B hat, it follows that the rank of T is less than or equal to n. In fact, we can do better than that. Since T of V1 equals all the way down to T of Vk is the 0 in W, and T of V k plus 1 is not 0 through T of Vn is not 0, the 0 in the codomain space. The theorem will be proved if we can show that the set T of Vk plus 1 through T of Vn is linearly independent. To this end, set the 0 in W to be C1, Ck plus 1, T of Vk plus 1 to Cn T of Vn. But that gives you, by linearity, T of Ck plus 1 Vk plus 1 through Cn Vn equal to 0, which implies Ck plus 1 Vk plus 1 through Cn Vn is in the null space of T. But wait a minute. Vk plus 1 through Vn are not in the span of that basis V1 through Vk for the null space. The only way this can be in the null space is if all of the constants are 0. Otherwise, this would have to be in the span of V1 through Vk, and so these would be not linearly independent of V1 through Vk. But we've assumed that B hat is a basis for the vector space V, the domain space. So these constants must be 0, and that implies that we have linear independence. That means T of Vk plus 1 through T of Vn is a basis. It spans the range and it's linearly independent. It's a basis for the range. Since this is a basis, that means the rank of the linear transformation T is n minus k. That's the elements there are in here. N minus k. Now let's trace this. Rank plus nullity. The rank we've just shown is n minus k. The nullity is the number of elements in the basis for the null space, which was k. And so we get n, which was the number of the elements in B hat, which was a basis for the domain. And that is the end of the proof. These concepts of rank and nullity have something to do with matrices. After all, we are pursuing a program of turning vector spaces into Rn, and another part of our program is to turn linear transformations into matrices. We need to know what's going on with matrices before we complete that program. So, let's suppose A is in the set of m by n matrices. Note that if A is in M, let's say 2, 3, it's 2 by 3, that means it has entries with 2 rows and 3 columns. That means the columns here are in R2. The columns here are in Rm. We're going to introduce a certain notation. L sub A of V is going to be A times V. In other words, L sub A will be a linear transformation, because matrix multiplication is a linear transformation, from Rn into Rm. Remember, when you take something that is m by n and multiply it by something that is n by 1, you end up with something that is m by 1. The domain will be in Rn. The range will be linear combinations of the columns, and the columns are all in Rm. So you're going to output things in the vector space Rm. Such a thing is a linear transformation, because if I take LA of kv plus w, I will get A times kv plus w which is KAV plus AW, or K times L of V, LA of V, plus LA of W. It's a linear transformation. Also, the range of such a thing is equal to the span of the column space of A. The span of the columns, that's the column space. We may as well make that a formal definition. The dimension of the column space. The column space of A is denoted by COL of A. The dimension of the column space is called the column rank of the matrix A. There are equivalent definitions for the rows of a matrix. The row space is the span of the rows. The row rank is the dimension of the row space. The row space is denoted by row of A. The dimension is the row rank. Note, the range of the linear transformation with matrix A is equal to the column space of the matrix A. That implies, by the Dim-Dom Theorem, that the dimension of the domain is the rank plus nullity, but the rank is the dimension of the range, that's the dimension of the column space, which is the column rank. Column rank plus nullity for some linear transformation defined by a matrix A. Right now, we have no reason to believe that the column rank and the row rank, the dimension of the span of the rows, are equal. In fact, they even live in different vector spaces. The columns live in Rm, the rows live in Rn. Why should the same rank? It's a theorem that the row rank is always equal to the column rank. The row rank equals the column rank in every instance. In our proof, consider this. The row rank is the number of non-zero rows in the reduced row echelon form of A. When you rewrite the rows, you're taking linear combinations. If you can get a linear combination that makes a row equal all zeros, then that row must have been dependent upon the others. So it's the number of non-zero rows in the reduced row echelon form of A. That's the number of leading ones. But how many leading ones do you have? Well, as many columns as you have, less the size of the null space. The nullity of the linear transformation using matrix A. The nullity is the number of free parameters that you have in constructing your solutions. By the Dim-Dom Theorem, that's equal to the rank. And the rank is equal to the dimension of the column space of A. And that's the column rank. Putting some things together from our discussion from today. Let A be n by n. The following are equivalent. 1. A is invertible. 2. AX equals 0 has only the trivial solution. Only the zero vector in the domain will map to the zero vector in the range. That says something about the nullity. The nullity of the linear transformation using the matrix A must in fact be 0. But if the nullity of the linear transformation defined by A is 0, then its rank of that linear transformation must be n. That means the row rank of A, n, and the column rank of A is n. Also, AX equals B has a unique solution for each B in Rn, which means that the range of the linear transformation using A as a matrix is all of Rn. Now, if the only solution to AX equals 0 is the trivial solution, that means the null space of this linear transformation is only the zero vector. The only way the row rank can be n is if the row space of the matrix A is all of Rn. Now, if the column space is Rn and there are n columns, that means the span of the columns is Rn, and that means that the columns are linearly independent and form a basis for Rn. Now, if the row space is all of Rn, that means the rows are linearly independent and form a basis for Rn. And that means the reduced row echelon form of A is the identity matrix. Each row will have a leading one. The number of leading ones, the number of pivot columns, in the reduced row echelon form of A is n. As you can see, the number of statements equivalent to a matrix having an inverse, meaning that the matrix is non-singular, is getting pretty long.